So as we enter chapter 6, we're going to shift gears a little bit. In the previous chapters, we've talked about chemical reactions and molecules and atomic structure and a lot of the math that was necessary for doing a bunch of the chemistry. In chapter 5, we talked about gases, and we did get into some chemical reactions. In chapter 6, we're going to look at thermochemistry. Now, thermochemistry is another part of chemistry that is related to chemical reactions. But so far, what we've looked at in chemical reactions is reactants react to form products. We've only looked at the molecules that react and the molecules that are produced. Well, also important in chemical reactions isn't just the molecules that are consumed or produced, but also the fact that in a chemical reaction, energy can be produced or energy can be consumed. And so that's going to lead us down the path of thermochemistry, which is the study of energy in chemistry. Now we're just going to do a very brief overview of thermochemistry, and if you go on to 102, you'll spend much more time with thermochemistry later. In order to start down this path of studying thermochemistry, we do need to look at some definitions. So we're just going to go through these definitions, so it's not the most visual slide in the world, but these are some definitions you need to know. You need to have these in your toolbox as we proceed through this chapter and through the future. The first thing for us to understand is what energy is. Energy is just the capacity to do work or produce heat. We'll look at both what work and heat are in a moment. We also have the law of conservation of energy. Now, the law of conservation energy is one of our physical laws. It's essentially just says that energy can be converted from one form to another, but it can't be created or destroyed. All right, energy is here. It's just going to be moved from one place to another. That's as much as can happen. The first law of thermodynamics is essentially another way of phrasing the law of conservation of energy. Energy of the universe is constant. The same way, so this is the same as the law of conservation of energy, and we'll see what that means as far as the energy of the universe versus the system that we're studying and everything else that we're not studying, and how that energy change of those things are related. We have two types of energy that we'll look at. One of them is potential energy, and potential energy is energy due to position. So when we think about it in terms of position, if you have a mass that's at a higher height than another mass, the one at the higher height has more potential energy. It has more potential to move across a distance. Now, there's also energy due to chemical composition. Now, this is also potential energy. It's essentially, we can think of it as energy associated with bonding. We also have kinetic energy. Now, we've looked at kinetic energy already. We've looked at it in gas chemistry as the energy associated with motion. In particular, the motion of, we looked at it for the motion of the gas particles, and we measured that kinetic energy through the temperature. Right? So temperature is just a property that reflects the kinetic energy of the particles, and we use something like a thermometer to measure that. It just tells us how those particles are moving. Now, with energy, we said energy is the capacity to do work or produce heat. So heat is actually a process, just like work is a process. So heat is a process that involves the transfer of energy due to a temperature difference. And so if you were to touch something at a higher temperature, you would feel, your nerves would detect that, and it would feel hot to you because the energy was transferring to your lower temperature fingers in a case where you're touching something. Work, another way that energy is transferred is by a force acting over a distance. Now we're going to look at it from the standpoint of pressure volume work associated with a system. And we'll see that in a slide or two. Another thing to think about is a pathway. Now, we're not going to spend as much time on a pathway, but it's basically, how does the energy change? Does it change as work? Does it change as heat? How does it get there? And that's something that is more important in sort of a higher level thermodynamics or thermochemistry course, it becomes a much bigger thing. So we're going to gloss over this a little bit in this case. Suffice to say that if you go on a bit farther in chemistry or physics, you'll see that in thermodynamics. A state function, right? A state function, not just a dinner at the White House, right? But a state function is just a property. It's actually a property that's independent of the pathway. Doesn't matter how you get there, it's independent of that pathway. So there are a bunch of different state functions for systems that are out there, and we'll explore some of these as we proceed as well. Okay. Work, for example, is not a state function. Work does matter how you do that work. Now, to describe a system. So a system, it's the thing we're interested in. It could be a chemical reaction. It could be a volume that has a gas in it. It could be a substance, a certain amount of a substance. But that's what a system is. The surroundings is everything else. Everything in the universe surrounding that system. It's basically, you have a system is the thing you're interested in, the surroundings is everything else, and we're going to phrase a lot of our discussion around those two things. We also have the internal energy of a system, and so that's just a property that, I guess this should be not delta E, but just E. It's a property that of a system that can be changed by the flow of work or heat, or both. Now we're going to look at internal energy and its relationship to some other thermodynamic properties as well. Chemical energy. Okay, so chemical energy is just the energy associated with bonds. So this is a potential energy or type of potential energy. And we think of it as heat in many cases. And then we have two processes, exothermic and endothermic processes, where exothermic is a process where energy flows out of the system. And if it flows out of the system, it's flowing into the surroundings. Whereas endothermic is a reaction or a process where heat flows into the system. And so if it's flowing into the system, it's going to be flowing from the surroundings into the system. Now, these are things that we're going to talk about as we go through the chapter. They'll come up here and there, but they're things that you need to have in your toolbox, in your vocabulary, as we start to study energy and as we continue to use our study of energy in chemistry. So let's start with the internal energy of a system. Okay. When we think about the internal energy of a system, and we said up here, we said the internal energy is a property of the system that can be changed by flow of work, heat, or both. So what it is, it's a property of a system that is really just the sum of each particle's energy in that given system. To change the internal energy of a system, you can do work or transfer energy as heat. But it's basically the change in internal energy of a system is the internal energy of the system before and after the process or reaction has occurred. And so we call that a delta E. And we can say, well, it's the final energy minus the initial energy. Or for a chemical reaction, the energy of the products minus the energy of the reactants. And so that's something we can track based on some thermodynamic data, and we will do so over the course of this chapter. Now, a system can change its internal energy in one of two directions, really. One, we can release energy into the surroundings, and in that case, the final energy will be less than the initial energy. Or we can do it by absorbing energy from the surroundings, in which case the final energy will be greater than the initial energy. So it can be done in either way, but that's how it's going. There's a transfer of energy from or to the surroundings, depending upon what the process or reaction is. Now, energy can be transferred in one of two forms. There's heat. Okay, so heat is something we're going to look at. We call that thermal energy. We'll look at this somewhat in depth in the next section in particular. But energy is transferred as a result of a temperature difference between a system and the surroundings. So that temperature difference may be sort of baked into the system. You may have a piece of ice that you put into some water, and the energy is transferred from the water to the ice as the water cools down. And you can describe that as maybe your ice is your system and your water is the surroundings, something like that. So that's already baked into the system, or you can consider that transfer of energy as a result of a temperature difference that occurs due to a process or a reaction. Right? If a reaction generates energy, that reaction is going to a higher temperature, and a lot of times that energy will dissipate as it goes out into its surroundings. The other way that energy can be transferred is via work, and so work is energy that's transferred when an object is moved by a force. So it's a force times a distance is how you do work on something. Now, when we look at the change in a system's energy, so if it can be transferred in either of these two ways, then we can think of the delta E as being equal to Q plus W. Now in chemistry, and largely in parts of physics, work is defined in the following ways. Basically, there are two important types of work in chemistry, okay? One of them is electrical work, which we're gonna not use here. We're not gonna look at electrical work so much here. That's more of something for Chem 102 in chapter, I believe it's 18 material, which is electrochemistry, where in that case, that's work that's being done by movement of charged particles, in particular electrons, say, flowing through a wire. So that's a particle that moves through a wire that does the electrical work. The other type of work, which is much more important for us here, is what we call pressure volume work. Okay, so pressure volume work is really just a mechanical work done when a volume of a system changes in the presence of a constant external pressure. So a way to think about this is, if you have a sample of a gas in here, maybe two gases in here, and a reaction occurs such that those gases cause products that take up a larger volume, then the gases on the inside can cause this piston to move up and expand. In that case, the gas is doing work on the surroundings, right? So there will be a positive value for the work based on the change in volume of the system. And so a way to look at this is, well, okay, so if we look at the work there, in that case, that's being done on the system, right? So we think about it as being work done on a system, okay? So if we think about work being done on a system, if the system does work on the surroundings, you're gonna have a delta V that is negative, or that is positive, right? So in this case, we're talking about delta V as positive. Right? And so it's being done with a constant external pressure. That's the pressure associated by the atmosphere here. Right? We know that this cylinder with the piston will move up until the pressure on each side of the cylinder is equal. And so we can think about the work done on the system as the negative of the pressure times the change in volume. And the reason for that is, if the change in volume is a positive value, the pressure is always going to be a positive value. And so if we think about the work being done on the system, we need that negative in there because the system is actually doing work on the surroundings. So that's what that's there for. And so when we think about this, this is what we consider pressure volume work. And we're going to spend very little time on this because the certain situations that we tend to look at in chemistry involve work that's very, very small compared to the work associated, or the energy associated with the overall process. Basically, work values are going to be so small as to be negligible for many of these systems that we look at, okay? And that's something sort of to keep in mind as we're going through this course and through this chapter. It's just, we're not dealing with work so much because we're going to be a little hand-wavy, but try to give you some reasons for this as we proceed through the rest of this chapter. Right? We're going to sort of neglect work a little bit because of some properties that we'll talk about as we move forward. But work that we talk about in this chapter is pressure volume work. Okay, so sort of put that pressure volume work in your back pocket, put this energy is equal to Q plus W, put that in your back pocket. We'll come back to that pretty soon. In section 6.2, this is enthalpy and calorimetry. So the first thing we need to know is what enthalpy is. Okay? So the enthalpy, it's a thermodynamic variable defined as, so this is a thermodynamic property. It's defined as the internal energy of a system plus the pressure, the product of the pressure times the volume. Okay? And this is for reactions at a constant pressure. That's kind of a key here, right? It's for reactions at a constant pressure. So when we think of enthalpy, we should always think, oh, this is a constant pressure thing. So you might be doing, looking at chemistry that's taking place at sea level, and you're always looking at it at sea level, so the pressure is always constant. That's the kind of thing we're talking about with enthalpy. So when it comes to enthalpy, though, a more useful thing for us to study is what we consider the change in enthalpy, because the change in enthalpy is something that is more easily measurable, and that's just the change in internal energy plus the product of pressure times the change in volume. Okay, and so here we can say enthalpy change is going to be the energy plus P delta V. So plus the pressure, which is constant, times the change in the volume of that system. Now, if we substitute negative P delta V for work into the internal energy equation, you'll notice that this changes things around a little bit. So if we think about, remember the internal energy equation that we put in our back pocket a moment ago? Delta E is equal to Q plus W. And if we think about what work is, right? Work is equal to negative P delta V. Right? So if we then plug in the negative P delta V into the work right there, we now get delta E is equal to Q plus W. And if we rearrange that, we can rearrange it so we can solve for Q. And if we do that, so in other words, if you add P delta V to either side, we'll see that Q is equal to the change in energy of the system plus the pressure times the change in volume. In other words, heat and enthalpy are the same for a system at a constant pressure, right? So heat is equal to delta H for a system at constant pressure. Okay, so we're going to consider those things to be largely equivalent. Now, there is another thing that I want to add to this, and so if you'll give me a moment. Okay, something else that I want to add to this is our understanding based on that Q is equal to delta H, which is equal to delta E plus P delta V. Under many cases, the enthalpy change of a system will be equal to the energy change of a system. Okay. And those cases are as follows. Right? For reactions where the reaction takes place in an aqueous solution or in a solution. And the reason for that is if I have a reaction that takes place in solution, well, the solution's volume, the delta V for that system, the delta V is going to equal 0. Therefore, the P delta V term goes to 0. And so when we think about a reaction in solution, the energy change of that reaction is going to be the same as the enthalpy change, which is the same as the heat. Okay, that's a big one. That's one that's really common, right? Chapter 4, we looked at aqueous reactions, and so we're going to run into those quite a bit. Another one is for reactions where the work or the delta V is very small, right? Thus, the work is very small compared to heat. So you can think about it this way. We're going to write out another equation here. If you think about delta E is equal to Q plus W, if the W is very small compared to Q, then Q is largely pretty much going to be the same as delta E. And that's going to occur for very many chemical reactions that occur where there's an exothermic or an endothermic reaction. The heat generated or given off or absorbed by a chemical reaction will just be much larger than the work is. And sort of hand wavy, the most hand wavy of these things that we're going to look at is if there is a delta V, that is larger, then in many cases, the work is still much smaller than the heat associated with the process, like a chemical reaction. Right, and so in many chemical reactions, that's something that we're just going to see, right? If the reaction gives off a lot of energy, well, even if that volume change is larger than in many other reactions, it's still going to be that the work is often small compared to the heat associated with that reaction. And so most of the cases that we're going to deal with, we're going to consider enthalpy and energy to be approximately the same. Now, when you get down to the nitty-gritty and details of it, that's not always the case, and you have to keep track of both things. But for much of what we're doing, that's a pretty good approximation. So let's look at some measurements of heat so we can measure energy changes of various systems. First off, we have a new definition, right? So calorimetry. It's just the science of measuring heat, right? So this is a process or a study of heat and how heat is related to chemical reactions and processes. Now we use a calorimeter which is a device for measuring the heat, and there are two main types of calorimeter. There's the coffee cup calorimeter, which you see here, and that's a pretty good calorimeter for many things that are done at a constant pressure. And we call it a coffee cup calorimeter because in many cases, those styrofoam coffee cups that are out there are the same substances that we use to make the calorimeter. You might take two coffee cups and nest one inside the other, and then put your system and everything that you want inside the coffee cups with a thermometer and a lid. The lid kind of keeps everything nice and intact. But essentially, this calorimeter is like its own little pseudo-universe, if you will. It's an insulated container that keeps all of the energy in that we can possibly keep in, right? So it's insulated container. The other type of a calorimeter that's out there, and these are things that we won't use quite as much, but it's a bomb calorimeter. Now, a bomb calorimeter looks like this piece of metal, and in here you've got the metal case, and inside you've got a little pan here, which is where you'd put your sample, and you would actually connect a wire. You'd put your sample inside here, and that would sit in this little wire holder, and you'd have a wire that connected to it and then connected to the other side. And what that wire would do is that would be your ignition source, so you could burn something, or you could essentially explode it. Because what you would do with this, and here's a diagram of the inside of one of these, is you would fill the inside of it with a bunch of oxygen, and you would cause a spark, and it would cause whatever you have in that container to essentially burn very efficiently, because there's an excess of oxygen. The oxygen would be the excess reactant. The heat generated inside this calorimeter would then be transferred to a water bath outside of a known volume or a known mass, and you could measure the temperature change of that water. And when you measured the temperature change of that water, you could tell how much energy was released in that combustion in this case. And so this is something that you could do for, say, food. If you wanted to see how many calories there are in a cookie, you could take a little sample of cookie, place it in the pan in here, fill the container with oxygen, spark the cookie, and it would all burn up. Now, it would probably be a bit more efficient than your digestive system, which obviously doesn't use all of the energy of the cookie in the same way. And so that's how you can measure the energy associated with some chemical reactions, right? You can do it in a coffee cup calorimeter, which is at a constant pressure, or you can do it in a bomb calorimeter. And a bomb calorimeter, because it's this metal container, right, it doesn't change its volume. This is going to be a constant volume calorimetry. Okay, and we call it a bomb because essentially that is a bomb. That's going to be a very, very high pressure system, which is why you need this very sturdy metal container. Now, when we do calorimetry, it's important that we have an understanding of what is called the heat capacity. And there are a couple different versions of heat capacity out there, okay? There's the heat capacity, there's specific heat capacity, and then there's going to be molar heat capacity. Now, if we look at the heat capacity, which is, as you can see, has the symbol capital C, this is for an object, and that's a key here. It's for an entire object. That object probably consists of many, many parts that could have their own heat capacities in and of themselves, but on the whole, the object has a heat capacity. For example, a calorimeter actually will absorb some heat. Even though we want it to be a good insulator, it does absorb some heat. So the calorimeter would have its own heat capacity, which we actually call the calorimeter constant. But that would be associated with, if we're looking at a coffee cup calorimeter, how much energy is associated with the change in temperature of the coffee cups, the thermometer, and the stirring rod that's used to stir up the reaction as it proceeds. And so to measure that, all that is, it's the amount of heat required to raise the temperature of the whole thing. So in this case, of the whole calorimeter by 1 degree Celsius. There's also the specific heat capacity, which is for an amount of a substance. And that's abbreviated C with a subscript S. And the amount of heat required to raise the temperature of 1 gram of the substance by 1 degree is what we call the specific heat capacity. So this is based on 1 gram of a substance raising its temperature per degree Celsius. So the C sub S, or the specific heat capacity, is the heat absorbed at constant pressure, divided by the mass of the sample times the change in temperature. We also have the molar heat capacity, which is related to the specific heat capacity through the molar mass. And that's really just the amount of heat required to raise a mole of a substance by 1 degree Celsius. And so it's the heat absorbed at constant pressure divided by moles of the sample times the change in temperature. Now, something else that we can use here, and one of the common equations that we'll see in calorimetry, is instead of saying the heat absorbed, we can actually solve for heat by saying Q is equal to M, or the mass of the substance, times C sub S delta T. Or Q is equal to N times C sub M delta T. Those are ways of doing chemical or some chemistry that is really useful to us, okay? And so calorimetry relies a lot on those particular processes, okay? So let's talk a little bit more about how calorimetry works. Now, one of the things that I want us to understand, when we do calorimetry, we consider a key thing here: the energy of the universe, which is equal to the energy of the system plus the energy of the surroundings, right, is going to be important in our understanding. But you can also look at, we can add in here, plus the energy of the calorimeter. if you want to separately say the calorimeter is part of this. Now, what you can do here now is say the change in energy of the universe during any process is going to equal the change in energy of the system plus the change in energy of the surroundings plus the change in energy of the calorimeter, it's an L, which is equal to 0, right? The energy of the universe isn't going to change. We will often approximate this, the energy of the energy change of the calorimeter as 0 as well, or often make the assumption that delta E of the calorimeter is equal to 0. Now, it's not always a good assumption, and experimentally we should always take that into account, but for the sake of the calculations that we will tend to do in this course, it's not a bad idea, okay? And so what we can do then is say the change in energy of the system plus the change in energy of the surroundings is equal to 0. Now, why is that important? Well, let's think about what we said our calorimeter is, right? We have our coffee cup calorimeter, for example, right? We have that one nested inside the next, and we have a top to it. We have our thermometer that goes in here. There are little tick marks in here. We have our stir rod, okay, to stir up whatever the sample is in here. And then we have stuff in there. Now, this is a calorimeter. We're considering the calorimeter to be, everything inside the calorimeter to kind of be in its own universe. Right? Or a pseudo universe, sort of parenthetically a universe. And why is that? Well, the calorimeter is a good insulator. And so if it's a good insulator, right, it doesn't allow heat in or out. Okay, thus delta E should equal 0 or close to it. And so with that in mind, what we can look at inside the calorimeter is generally the water, and that's part of this, but there's water and there's also either a reaction or maybe an object, right? And so, for example, if we said we had, let's say an object, we put in a piece of metal at a temperature that's higher than the temperature of water. Right, then the process of heat is you're going to get energy is going to transfer as heat from the metal to the water. Right, so in that case, you can say you can define it. Let's say the metal, we'll call the metal our system, and the water is the surroundings. In that case, we can say the delta E of the metal plus delta E of the water will equal 0, or delta E, of the metal will equal negative delta E of the water. And I can even simplify this a little bit more to make it useful for us. We can say the Q of the metal is equal to negative Q of the water, right? And that's how you can do some calorimetry. We can measure the heat that's absorbed by the water in order to figure out the heat that's given off by the metal, because we can determine that the mass, remember Q is equal to the mass of the water, times C sub S for the water, so the specific heat of the water, times delta T. And so you can do that for the water, and that you can use that in the calorimetry, right, to your advantage, okay? That's for a process, right? We can also look at calorimetry for a reaction. Okay, so let's think about a reaction. If we have a reaction where we have reactants that react to form products, we can have an enthalpy change. We call that delta H of reaction. Okay, so if the delta H of the reaction is greater than 0, we call that endothermic. If we have reactants that go to form products, and we have an enthalpy change for a reaction, which is, remember, the heat given off due to the reaction. For example, combustion is a very exothermic reaction. The delta H of the reaction is going to be less than 0, because the thing that we're burning, its energy is going down as energy is released to the surroundings. That's why we feel the heat from combustion. So that'll be an exothermic reaction. So that's something that we will see for chemical reactions. Now, what's useful for us here is that if we think about a chemical reaction that occurs, let's say, in a calorimeter, right? So if we have our calorimeter now, we have our water in here, right? We got a thermometer, we're taking the temperature, we're stirring it, right? You have water here. What about if you have a reaction, right? And so that's something that you can look at as being, well, the energy associated, or the energy change associated with the reaction. We can call that the delta H of the reaction, the heat associated with the reaction, or the enthalpy associated with the reaction, plus the heat associated with the water. Those two things, when you add those up, are going to be equal to 0, right? And of course, that water is the water that's in the calorimeter. So if you have an acid-base reaction that occurs in the water, the acid and the base react, and the temperature of the water often goes up. And so you can measure the amount of energy that's associated with a chemical reaction that takes place in that calorimeter by how much, by first off, how many moles react of the reactants, and also how much water you have and the temperature change of that water. And so for that, you can say the enthalpy change of the reaction will equal negative Q of the water, which will equal negative MC delta T. And then what you can do is you can figure out the molar enthalpy change. Right, which would just be the enthalpy change of the reaction divided by the moles reacted. Right? And so you could figure that out for a given reaction, and we can use this to analyze reactions, and that's something we're going to do as we go through the future. But that's how you would determine the enthalpy change of a reaction. So that's going to be used in thermochemistry. Okay. All right, and so we're gonna take a pause here, and we'll come back and we'll do this particular example problem to illustrate how calorimetry can be done in an experimental setting with a certain amount of data.